All right. Hello, everyone. Welcome to the Off by One Security channel. With us this week, we've got the amazing Connor McGarr back for, I believe, the third time. He's been so kind enough to join us here and share his knowledge. So always a pleasure to have Connor join. The session today, it's titled Windows Secure Calls in Practice, VSM, VTLs, and SkBridge. And it's a fascinating area where it's funny, a lot of times on interviews when I get involved in them, especially when like malware is involved and such, and you're talking to somebody who's used different tools to acquire active, running memory and things like that, doing memory acquisition. I oftentimes will ask the question around, okay, so if you're dealing with a situation where malware is running as an isolated user mode process, are you able to use tools like volatility to acquire that the same way that you would regularly? And it's a question that often stumps people because obviously getting into a hypervisor world and just like the brokerage and connectivity through it, especially when going back to things like credential guard, where LSAS has moved over to the secure kernel instances like lsaio.exe, and it's encrypted now. Just brings up some interesting technology and such. We also had, oh shoot, the name is slipping my mind, but I'm going to post it up in the chat here soon. On talking about their product that allows you to do like JTAG debugging and be able to interact with the secure kernel and such. So as usual, I will be quiet here and let Connor, who's much more of an expert in that specific space for sure. Connor, I know most folks probably know you, but you want to do a quick introduction on yourself?
Yep, and I think the name you're looking for is Alan.
Alan
From SourcePoint.
S.
Yeah, Alan. Yeah, great person. Yeah, he gave me that JTAG debugger for testing at some point. So yeah, great guy. But anyways, yeah, I'm Connor. I work in a security startup called Origin, which is by a larger startup, I guess you could say, called Prelude Security. And I'm primarily just interested in Windows debugging, kernel, C, hypervisors, all the typical fun stuff. I like building out tools, writing blog posts, giving conference talks, etc. So that's that's pretty much me in a nutshell, I'd say.
Yeah, thanks again for your blog. I always hear so many people, especially on our Discord server and such, say, oh, Connor was nice enough to look at the research I was looking at and everything. So I know it gets referenced quite a bit, so much appreciated. Yeah, so I guess what was kind of your goal in looking at this area? Was it just looking at a new attack surface and trying to find vulnerabilities, or just a deeper understanding on how it works, or all of the above?
Yeah, so it actually started with Alan, who reached out to me and mentioned, hey, I have this cool debugger. It can debug secure kernel. You can do hypervisor debugging without JTAG, but just in general. Gave me this tool, and I thought, okay, now is a good time for me to do dynamic analysis in secure kernel, because that's the most difficult part. There are blogs that are out there about debugging the secure kernel. You can definitely dump memory and things of that nature, but actually setting breakpoints, walking through code, all of that stuff becomes very difficult without something like a JTAG debugger for production release of secure kernel, that is. And so it started there, and I thought, all right, this is a good opportunity to put this all to the test. And as with anything with secure or with debugging in general, it's a repeated process. You're constantly repeating. Well, to talk to the secure kernel, as we'll see in some of the demos that I'll have, one of the primary methods is whenever kernel mode in the traditional kernel invokes a hypercall, and that execution gets sent to the secure kernel. Well, when you're constantly recompiling driver and loading it and starting it, that gets very, very laborious, I guess you could say. And so I decided to basically write some tooling to automate a lot of that process, which I'll demonstrate as well. Then on the flip side of that, I thought, okay, that's very cool that I can do all this fun stuff. And of course, my reverse engineering and research and stuff, I saw, oh, there's actually completely undocumented ETW events. There's some of this other stuff, the data types themselves, the structure of the data, how to actually enable them, completely undocumented. So I thought, all right, well, I'll write the corresponding tool that can actually capture some of these transitions between VTLs, so to speak. And so then it turned into this big big thing. And I thought, okay, it'd be interesting to write a blog on it. And I think there's a big misunderstanding too with a lot of folks. A lot of people think Secure Kernel runs in the hypervisor, or Secure Kernel is the hypervisor, or things like that, which is not really the case. But yeah, that was kind of the gist of where this research came from. I did it a few months ago now. And also, I've been interested in Windows on ARM lately too. Really unexplored space, I would say. And so using this tooling, which I'm not going to have time to show today on ARM, I'll call out some of the nuances, also allowed me to test some of this stuff on ARM machines as well. So that's pretty much where all this came from.
Nice. Yeah. Now, individual DM me like 3 times on Discord leading up to your talk to say, make sure you ask Connor what his thoughts are on the future of kernel exploitation. And do you think that read-write primitives will still be there going forward, or are the mitigations getting so good now where it's just not even worth looking at?
Yeah, it's a great question. As any wise person would answer, it depends. And what I mean by that is, if you're talking traditional, old school, I'm going to take some shell code, I'm going to shove it in the kernel, and then I'm going to make this memory, executable and then execute it. That's not going to happen really. Because again, there's not very many times where you can say this is impossible. One of those times is with HVCI as an example, which I've talked about before. It is just impossible in the traditional sense. Again, there are things which are out of scope of HVCI, but the traditional, I'm going to corrupt the page table entry, make it executable, and then execute some memory. That's not going to happen anymore. But how do you get to that point? You need read-write primitives and all this other thing. So to answer the larger, more broad question, there is always going to be kernel exploits which exist. And it's not even necessarily that they're going to get harder per se. I mean, there are probably millions of drivers out there for Windows, as an example. So I think a lot of the times when you hear are kernel exploits going to be possible in the future, there's the taking advantage of drivers which aren't on every single machine in the world, but are out there, depending on the org or whatever. Those are always going to exist. I mean, there's probably so many, physical memory primitives and whatnot that just exist out there for keyboards and monitors and all that stuff. Then you have am I going to exploit Windows directly, through the interfaces, system call interfaces, filter drivers, whatever. It's obviously harder with mitigations that are involved. I think Microsoft as a whole has really taken a step back from just, adding on mitigations, and kind of taking a more nuanced approach, I guess you could say, to completely kill classes in general, not from mitigations, but from re-architecture, as an example. I mean, one of the things that we can see is with the new Windows endpoint security platform, or whatever it's coming out, WESP, that Microsoft has talked about, where a lot of vendors, as an example, are going to come face-to-face with user mode instead of kernel mode for getting some of this telemetry and whatnot. That as an example, just this whole architectural shift is the point that I'm making. Instead of just going, let's make another mitigation, make another mitigation, make another mitigation. So it'll definitely be possible. I don't think it's any harder now than it was maybe a year ago or 2 years ago. I think some of the more difficult is when you go back to, maybe 2015, 2016, when HVCI and whatnot are first coming out. Many people forget that. It's like, oh, HVCI, this new thing. It's actually a decade old at this point, a little older. Not many people adopt it at that point. But as time goes on, people get better hardware. Corporations get access to better hardware. People upgrade their laptops. The latest and greatest Windows machines have a lot of these mitigations enabled by default. I think in the next, few years to come, it will get harder, not necessarily because the primitives aren't there, but some of the mitigations like HVCI that maybe you don't see everywhere will be more widely adopted. And then you just have a bunch of stuff in general. Like I said, Win32k has a Rust equivalent now. I am a believer in Rust in the sense that, just putting something in Rust doesn't necessarily fix everything, but it's one of those things where definitely Rust has obviously thought about a lot of these memory safety type problems before. So we see things going into Rust as an example in this space will make things probably harder, but there will always be bugs because software is written by humans for the most part right now anyway. And Yeah, that's my view on the matter. But as things get harder, you see less public research, which is one of the counterparts to this, right? You don't see as many people as there was 10 years ago putting out a blog. Hey, here's this exploit end to end, as an example. And when you have less of that, it kind of creates this sense that those exploits don't exist, but really they're just privatized to folks who don't have an incentive to make this research public so that they can keep finding bugs for bug bounties for operations and all of that stuff is my thoughts on the matter.
Yeah, especially when those bounties get up into the millions of dollars, of course. It's interesting. I was reading an article the other day talking about how, unfortunately, with AI, the dependency on AI, smart devices, all that this is the first time in history that the average IQ of people in the West is going to start declining, which is a terrifying thought. But then it went into the fact that, like, think college students now using AI to write their code or write their papers and submit it. Like, if you're not doing the actual work anymore, there's not going to be many people who can question AI when it's wrong or when it's when it's hallucinating, when it's that. So I think being someone who really wants to dig in, even if you don't have to, and understanding what's happening under the hood very deep technically and doing the research like you do is going to be something that makes you increasingly valuable going forward.
Yeah, absolutely. The kind of canonical example for that is people always make the joke about, old banking software that, like, there's only, a handful of people that know this programming language anymore, COBOL and whatnot. Time will tell if that's if that's analogous to what's going to happen in the future, where, you have all these people using AI and vibe coding or anything like this. Are there going to be a handful of people who solve the issues, or maybe AI will solve them? For now, though, definitely, I'm always a proponent of tinkering, being curious, doing research, messing around. I think makes anybody valuable in general, because even if you're not doing vibe coding or anything like that, the presence of mind, the wherewithal to go, is what's being produced correct or not, or is it on the right track? If you don't have that foundational skill for now, it's going to be very hard to make those decisions.
Yeah, for sure. I'll let you get started here so we move on. But before that, one last question, because somebody posted it. Connor and I were actually talking a little bit about AI before we got started here. And if you watched the stream last week with Elias or All Things IDA, he showed some amazing, cool vibe coding with using Binja and IDA Pro, like headlessly, and using WinDebug, and just super cool stuff. So I guess what are your thoughts on using AI currently? Is that something you're leveraging a lot of or getting more into?
If I do use AI, it's just more of a, what do you think about this, or how does this sound to you? I am ignorant when it comes to many of the other things. Like, I know people are, oh, I plugged this MCP server into this and I, was control. I don't know anything about that at all whatsoever. If I use AI, it's just prompts, as an example, which sounds very lame, probably, like disappointing for some people to hear that. But for me, that's just where I'm at with it. There are some things that I will ask AI, but that's the extent of my use of it. But I'm also not, as we were talking about before, I'm not someone who says, oh, well, don't use AI, it's dumb. That would be, that's not true. There's two ends of the spectrum. And so I do think it is a useful tool for, people to leverage and people to tinker with. And I think it's, great in the innovation space. But for me, a lot of it, maybe I'll get left behind. I'm just so used to, manually doing a lot of my own research and whatnot, because I have a certain workflow. And then, same thing with people who maybe are afraid to fly, right? Like, no amount of someone telling you, hey, planes are more safe than automobiles, it's a control thing, right? You don't have control, you're letting someone else do it. And I think that's a big thing for me, probably too. Maybe as time goes on, I'll dig into it more.
Yeah, I mean, to be fair, AI is probably leveraging the research you're talking about today, so it knows how to do that stuff. So
yeah, maybe so. Yeah.
Cool. All right. Well, if you want to share your screen, we get
Yep,
started.
absolutely. So I figured it's probably best to just start out with a basic overview of, like, the current architecture on Windows. So I'll just go ahead and share a blank screen for now.
You're going to use your amazing Microsoft Paint skills.
Yeah. I'm actually going to use Zoom It for this one.
Right.
So, On traditional Windows systems, you know, we have kernel mode, we have user mode, and you know, all of your apps are up here, you know, 1.exe, blah, blah. And then let's say you have your subsystems down here. Let's say this is a higher level, like, you know, executive. So you have your, you know, kernel mode routine. So like your system call handlers, all that stuff. Memory manager, all that fun stuff. And then it just keeps going down and down and down, right? So this is traditional user mode, kernel mode, Windows architecture, pre-2015, there's abouts. Anyone who knows me knows I'm very interested in the mitigations under virtualization-based security. And what that does basically is it takes this traditional setup that we have here and it isolates it. So now you can think of this as in a VM, so to speak. Why do we want to do that? Why do we care about that? Let's think about one attack vector as an example. So we have here, let's say, let's turn this back to purple, a page table entry, some of the exploitation I was talking about earlier. And this page table entry says this memory that's described by this, well, I shouldn't say described, mapped by this PTE is readable and writable. So let's say that this memory represents some kernel mode memory. Let's say it represents the address, you know, FFFF78000000, blah. This memory address, this virtual address, is readable and writable. Well, if I have a kernel exploit, as an example, and I'm able to use a read-write primitive to locate this PTE, and I say, actually, I don't want this PTE to be readable, writable anymore. I also want to make this page executable now. Because all of these PTEs are managed by kernel mode, nothing is stopping an attacker with a kernel mode read-write primitive from corrupting these page table entries and then allowing execution to occur in this address. So there's a problem here. First of all, obviously there's a vulnerability, but the larger problem in general is that kernel mode is king. Once you're in kernel mode, that's it. You know, there's nothing else to be done. Well, there's actually something that we can do about this. And what we can actually do about this is we virtualize the operating system. So now we have something called root partition, which contains your traditional user mode, kernel mode. So you have this traditional user mode and kernel mode isolated in this physical address space. So this is a physical address space right here, the root partition. But then we can do something else. We no longer just have user mode and kernel mode. We can divide it. We can divide it into what's called VTLs. So we have VTL0 and VTL1. So what happens is you have kernel mode in VTL1 and you have kernel mode in VTL0. One is not more inherently privileged than the other. What is kernel mode? Kernel mode is simply when a processor, when its code segment in the case of code is executing at a current privilege level of 0 on x86 systems or exception level 1 on ARM systems. On most operating systems, there's some nuance to that. So it's not more inherently privileged, but what we can actually do is we can put VTL1 in its own physical address space, and we can put VTL0 in its own physical address space. So they're VMs. So you can actually think of VTLs as VM0 or VM1. Now, again, there's nuance to this. It's not that these are the exact same as a traditional VM, with all these para-virtualized devices, all of that stuff. There's enlightenments, there's, other things such as that. But the reason why we do this now is because we can operate as a virtual machine. So if we go back to our previous example, right, we have VTL0. VTL stands for virtual trust level, okay? And we have user mode and we have kernel mode. If we come back to our example where we had this PTE down here, this page table entry, which describes the page as readable and writable only. And then we have exploit.exe. which does a kernel mode read-write primitive, and it corrupts this to make it executable. We are now accessing memory inside of a VM of sorts. So what happens is we actually have to get the hypervisor involved. Hyper-V, which is lower level. So this memory access is gated by something called second layer address translation. Why?
Somebody just asked what SLAT is. That's good timing.
Yeah. Second level address translation. Why do we have to do this? Because let's say we have a VM. So as an example, I'll draw this example over here. This is the whole OS. So forget this for a second. This is divided up. This is its own thing going on over here. We have a VM. And here's all the physical addresses of the VM. What it thinks is 0. What it thinks is 1,000. What it thinks is 2,000. What it thinks is 3,000. What it thinks is 4,000, right? But that's located in an actual, this is located in an actual operating system. Host OS. Host OS, this is the real 1,000. This is the real 2,000. This is the real 3,000. This is the real 4,000. This is the real 5,000. So we can see if this is 5,000 right here, physical address 5,000, the VM accesses what it thinks is physical address 1,000. But this is in context of the VM. Something has to perform the translation from 1,000 to actually go, oh, actually the memory you're trying to access VM is actually located at 5,000. That's what SLAT does. There's a secondary set of page tables maintained by the hypervisor that contains all those mappings, and it's a per VM structure, the SLAT table. It's located on x86 systems as the extended page table pointer, or EPTP, and what's called the virtual machine control structure, which defines basically a VM or its resources. So we can actually do the same thing here. What happens is VTLs have all of their memory what's called identity mapped. So VTL 0 has, physical address 1,000, 2,000, 3,000. That is actually mapped to true physical address 1,000, 2,000, 3,000. But because we're using virtualization technologies, even though we don't need to perform a level of translation in the sense of actually getting the memory address, we still go through the hypervisor because that's what the spec calls for. We still go through the hypervisor. Well, what happens is with a mitigation like HVCI, all of the SLAT entries never contain dynamically executable code. What that means is it's write XOR execute in kernel mode. So the SLAT table for VTL 0 that says here's the true definition of memory for all of VTL 0 contains no memory, which is both writable and executable at the same time. What do you need for shellcode? If I have an exploit and I want to write shellcode to kernel mode, it needs to be writable. But that doesn't help me because now I need to execute it. So that writable code now needs to become executable. That execution or that memory access now goes through the hypervisor instead of just delegating it to the OS. The hypervisor then has a chance to go, whoa, hold on a second here. The actual SLAT table entry, the true view of memory, says that this page, which is readable, writable, and executable in kernel mode, actually is only readable and writable in the SLAT table for VTL 0 or this VM. And then what that allows is for the hypervisor to basically inject an interrupt into the secure kernel, which then can crash VTL 0 as an example, or just inject, I should say, an interrupt and crash the system. So what's the point of this? Why is this relevant? Why do I bring this up? The OS has been fundamentally re-architected for the last decade to protect sensitive resources like the page table entries. We don't let kernel mode in VTL 0 anymore be the arbiter of what is true and what's not true. So how does this work then? Who's the arbiter, or how does this all work? Well, Hyper-V is at a lower level. It's isolated, the hypervisor, and so it contains the final source of truth for everything. But who tells the hypervisor in the first place what to do? This is exactly where secure kernel and what we're going to be talking about today comes into play. So take, for instance, I talked about this in my Black Hat talk, but take, for instance, VTL 0. VTL1. So this is the secure kernel running over here. VTL0 is responsible for initializing something called kernel control flow guard, which is control flow guard in kernel mode. So VTL0 decides where is the KCFG bitmap going to reside, as an example. Well, once that information has been decided, this information has to be sent somewhere else. So it gets sent to the secure kernel running in VTL1. Then you have let me put the hypervisor. So this information says, hey, secure kernel, I'm letting you know the CFG bitmap is going to be located here. Then the secure kernel has to protect that bitmap to make it read-only in the slat entries like we talked about earlier. Say, hey, this bitmap is read-only and do not let anybody modify it, as an example. What the secure kernel does then is it has to go to Hyper-V and it has to issue a specific hypercall to say, mark this memory as read-only. How did VTL0 talk to VTL1 if these are completely isolated from each other? Because they're isolated as VMs are in their own physical address spaces. This is basically what we're going to be talking about today. One of the methods to do this is called the secure call interface. And it's brokered by Hyper-V. This is what I talk about in my blog. And so what I'm going to do now is stop sharing. And if there's questions as I'm facilitating to the next screen, please feel free to let me know. But basically the gist of this is the operating system is broken out into VTLs. You have the secure kernel, which is kernel mode in VTL1, and you have normal, kernel mode in VTL0, which is what you operate with on a day-to-day basis. It's what you see, it's what you interface with. VTLs have to talk to each other sometimes, especially when VTL0 has a resource that needs to be protected by VTL1, such as memory, etc. That has to get somehow sent to the secure kernel. And the secure kernel can actually talk back to VTL0 through something called the normal call interface, which we'll talk about as well. So even though these are broken out, there's still some level of interaction between them, which is interesting from a security perspective, right? Because if you're able to interface or get VTL1 or 0 to operate on data that you control, could be interesting from a security perspective. So what we're going to be doing is going through now what this looks like. I'm going to start out by sharing my screen with Hyper-V, some of the reverse engineering I did to show exactly what happens when Hyper-V first gets involved. But if there's questions, let me know while I'm facilitating, please, because I know that was a lot to chew on right there.
Have there been any notable findings or vulnerabilities in any of the brokerage kind of between the two VTLs areas or the hypervisor?
There has been. There's actually talk at Black Hat from 2020, I think during COVID, by Sarah Marr, who was part of MSRC, now works for Apple, I think. And he and Daniel King, I think it was from Microsoft, talked about 2 or 3 vulnerabilities that they found by basically going from VTL to VTL. Kind of using this similar thing. They had an internal tooling is what they talked about to do some of this fuzzing, which I hope is what the tool, which I'll share, SkBridge, is a public version of people doing that in the future. And they talk about some of the vulnerabilities. I'll talk about some of the common patterns as well of how, things get marshaled in and out. But they found 2 or 3 CVEs, I believe. I think it was 2020 was their talk. It was when Black Hat was virtual.
There's some more philosophical questions that we'll save for the end, but related to what you just said, someone's asking, does VTL1 kernel space, does VTL1 have control over the memory of VTL0? Is it also the case for user modes?
Yeah, so it depends is the word. So a really good example of this is something called VBS enclaves, which I'll talk about in a little bit. Enclaves used to allow, it's basically a DLL loaded into isolated user mode in VTL1. It's allowed to access the memory of its hosting process in VTL0. But now there are mitigations that exist from a few months ago where that's not the case. And you can actually prevent that memory. So in that case, no. But normally speaking, what happens is because they're in isolated regions of physical memory, they can't, but they can map. So secure kernel, a lot of the time, one of the common patterns is the physical address of a given memory address. So let's say you have a shadow stack. You say, hey, secure kernel, I need you to do something about this. The physical address is shipped to the secure kernel, and then the secure kernel can map it into its virtual address space, do whatever it needs to do, and that gets reflected in the physical memory. That's normally the common pattern. Can you see this, what I'm sharing? Or no? Oh, there it goes. Okay. So what I'm going to start out at is the VM exit handler. So what happens when VTL0 requests the services of VTL1 in kernel mode? This is the secure call interface. This is all done using hypercalls. So hypercalls we can think of as system calls for a VM. So a system call, traditionally speaking, is, user mode needs to request the services kernel mode. System call happens, transition happens, the processor starts executing in kernel mode, and then some output is returned back. There's a lot more nuance to hypercalls. It is not just, system calls. There's a lot more to it. But the overall gist is a given processor can execute in 2 modes on x86, which is what we'll keep with. We'll save ARM for some other time. It can execute in context of a VM or in context of the monitoring software, which is the hypervisor. A hypercall basically transitions execution. It does a VM exit, what's called. So the processor exits the VM. It starts executing in context of Hyper-V or whatever your hypervisor is. And then there's a VM return, which you can go back and start executing back in context of a V, or VM enter, excuse me. So all of this starts at the VM exit handler. Now I go over in my blog how to actually locate the VM exit handler. It's different on ARM, but on x86, the easiest way that I have found for Hyper-V specifically is if you go to the open subviews and you go to strings, dispatch, you search for the word dispatch, or maybe it's minimal loop. Yeah, it's minimal loop. Minimal loop has a few strings in here, and one of them is VM exit reason init int r. That's basically the way, it's a really cheap way to do it. There are other ways that you can find the VM exit handler, but that's normally the way that I do it for Hyper-V on x86 systems. This is minimal loop, which is handling all the various VM exit reasons, which I'll get into in a second. This is probably where the handler is. And that's exactly what this is. So basically, the main thing to think about here is that there's something called a virtual processor. When VMs are running, they maintain a virtual processor. And what that means is, right, if you have 3 VMs, as an example, they aren't all running at the same time. They take turns, there's scheduling involved, what have you. The VM processor represents kind of like a context record for a thread, as an example. Here's the state of this running thread or this suspended thread, or, it has to be suspended to get it. Same thing for virtual processor. It represents, here's all the registers, here's all now VTL information for this processor, as an example, and maintains state, right? So what happens is, and I've commented this, and you'll see a lot of this output looks really funky. Hyper-V does not ship with symbols, for those who don't know. So it's completely black box for the most part, which makes it difficult for reverse engineering. I won't spend too much time on this. There are blogs out there on hypervisor software and whatnot. But basically, 2 things happen. One, you have to get the instruction pointer of the instruction in the VM, which calls the exit, because you have to jump over it because you don't want to re-enter where the instruction was and allow the execution to keep going there. Sorry, my dog in the background. And then you get the reason for the exit. Why did this VM exit occur? So in this case, the VM exit, I guess we can click on it actually, VM read reads from the current VM's VMCS structure. And there are specific codes for each various item or field from the structure. VMCS exit reason is this. However, there's also an enlightened VMCS, because it's nice not to have to do an opcode to go fetch the VMCS every time. You can basically cache this, for lack of a better term. So in the GS segment register at this offset, we can find the VMCS, and this is the field for exit reason as well. So depending on if enlightenments are in use or not. So we have all these exit reasons, right? Again, go back to what we were originally doing. What are we talking about? We're talking about when VTL0 executes some kind of secure call to talk to VTL1. So execution is now here for the secure call. We go through all of the various exit reasons, and we come to this one right here called VM call. VM call is the opcode for a hypercall. So anytime a VM exit happens and the reason for it happening was a hypercall, this function will be called. So we go to this function, which is the handle VM call. There are further hypercalls to investigate. So we have the VM exit reason, which gets parsed in a large switch case, as we saw. But then we have to understand what kind of hypercall is being invoked, just like a system call. So we go through, and there's all these various hypercalls. Again, these are not part of the data in Hyper-V. I've imported them into IDA. So you have all these various hypercalls that can be handled. In this case, we are interested in the VTL call, which is the fancy word for VTL transitions. So anytime a VTL call or a secure call happens, the handle secure call handler will be invoked. But then we also have hypercalls, which can result in a return. So when VTL wants to start executing back and VTL1 goes to VTL0, that's through the secure return or VTL return interface. So in this case, we're interested in secure call because at the bottom, the actual secure call or return happens depending on the handler. So in this case, we have the secure call. We have the virtual processor, again, which is not a documented structure. It's just something that I've reverse engineered. And then this random bool right here. So as part of the virtual processor, each virtual processor, which runs on all physical processors, now has VTL information. So we get the current VTL, and then we determine the VTL that we want to go to. And we say, is that VTL initialized? One thing to call out here is I believe this is the case, but there's no way really for me to test it at the current moment because there's only 2 VTLs enabled. Azure has a third, which is VTL2. But there's 16 VTLs you can technically interface with. You can only go one at a time. So I don't think VTL0 can just call into VTL 15. I think you have to incrementally go up each one. So then, as I mentioned before, we have to get the RIP updated in the guest, and then we begin this transition of VTLs. And here's secure call return right here as well. Begin VTL transition, again, processor number, we get the current VTL, and we compare it to the target VTL. Some undocumented things go on here. You could probably go on for a while and figure out what all this is, but it's not relevant for our purposes. We then perform the transition itself. So this is where the bread and butter of everything comes in. The transition itself basically goes to the VTL array because, again, as I talked about, there's multiple VTLs. It's not just VTL0 and VTL1, although that's what we have today. We get the data, the VTL data. Each virtual processor has VTL data associated with it. Private registers, some of this other information. We update the current VTL to the target. And then what we do is we update to the new VMCS, which is the main thing that happens here. So VTL has private VTL data. Each virtual processor has VTL data, but then that data has additional private data, which you would have to fully reverse engineer. I'm not currently interested in it for our purposes. And effectively what happens is the VMCS is updated. So VMCS represents a given VM. So when you do a hypercall, when you do a secure call, there's a hypercall. The hypercall gets handled into this VTL call, specific hypercall code. All that does is switch the running VMCS from VTL0 to VTL1 and hands off the parameters which were passed, which were encapsulated in an MDL or physical memory. So again, back to what I said earlier about people a lot of the times misunderstanding. Hyper-V is just the broker. Secure kernel does not run in the hypervisor. Hyper-V is the broker. Secure kernel runs just as VTL0 runs in its own isolated region of physical memory. Now, there's nuance. Secure kernel has no way to do file I/O. Those functions don't exist. Those system calls don't exist, as we'll see. It doesn't do networking. So even when you see researchers talk about getting code execution in VTL1, there's not a whole lot that you can do there. It's an interesting thing because it's different, but there's not a whole lot that you can do there from networking perspective or anything of that nature. And this is the VM pointer, basically does the unenlightened version of updating the VMCS itself. So that's Hyper-V in a nutshell. Again, VTL0 makes a secure call. That does a hypercall to Hyper-V. Hyper-V updates the VMCS of that target processor to that of VTL1, which is secure kernel. Then secure kernel has a large dispatch loop, which I'll show here shortly, which then actually performs the operation itself. So I will go ahead and stop sharing the Hyper-V IDA, and we'll open the Secure Kernel one. And I promise what I'll do at the end is I'm trying to articulate here's how this works. Then I will go back to NT and show here's exactly how the secure call gets set up, and then show you how my tool can do it for you too, and why it's relevant. If there's questions, let me know, please.
Yeah, there's a few questions. I don't know if there might be things that you're going to cover, so I can ask, and you can. I'll put it up on the screen. It's in cover Discord, but it's how our secure call ID is mapped to the secure. You can read it.
Yeah. No, exactly. That's what I'll show. They're actually tracked by a symbol in NT, which you're going to see right here when I start sharing this screen. And what's tricky is this. You can have a secure call number of like 200. 200 may not be the same secure call on another version. Like, even though 200 might exist, 200 on this machine might be shadow stack assist, but on this machine, on this version of Windows might be, image update or image load or whatever. It's very confusing. It's not like system calls where, stuff will get added in. But normally, generally speaking, the system call numbers don't change all that much, although they can. I'm not saying that they don't. But I'll share that right here.
And some of the questions I'll hold off on because I think you're going to cover it. One that's relative to what you were just asking. I think it's a pretty simple question, but is there any difference between how VMware runs two VMs to how Hyper-V implements VTL0 and 1?
Yes, there is a difference because VMware is a type 2 hypervisor for the most part, whereas Hyper-V actually ships with the operating system itself. And so on ARM machines actually do this. If anyone's familiar with Trusted Zone on ARM, at least on like Qualcomm systems, they have their own proprietary hypervisor, which can basically break out the operating system similar to what we're talking about here. VMware is not capable of doing the same thing because all of this instantiating of the VTLs and whatnot happens as the OS itself is booting. So it's very much in the core of the OS, the hypervisor is involved. Whereas VMware is more of a post, boot install thing, so to speak. And a lot of that is para-virtualized, which is why you see a lot of the times better performance with Hyper-V as an example, because it's native to the OS. As an example. But again, we could go on for hours about this. There's tons of nuance to everything I'm saying. There's probably some hardcore hypervisor person's like, rabble. I know there's nuance to this, but it's impossible to cover everything. But for the most part, no, it can't work the same. Again, everyone will probably laugh at me that I failed in my decompilation, but when you see how large this function is, I didn't have time to go through everything. So this is the main handler in the secure kernel. So what happens is, Secure Kernel has a dedicated thread or set of threads that handles entries from. What happens is every time the Secure Kernel does a VM exit or a secure call return, it fixes up execution so that when that VM is paused, so to speak, and it re-enters, the entry point is basically here at this IM invoke secure service. It's not always here. It's actually in a wrapper higher up. It's called like SK handle normal call RAX or some random function like that. But basically, there's this song and dance that's done every time this VM is about to exit or it's done doing whatever it needs to do to where execution is fixed up. But what happens is for secure services, which gets called by this SK call normal mode in some instances, but also it's in other places too. And my blog does an active debugging of the secure kernel to go through this whole song and dance. But for us, we need to, kind of speed things up. This is an undocumented structure, which is in my secure call SkBridge project, which represents a secure call. It's kind of talked about in Windows internals part 2, but there's also some fields which are missing there. And this IUM invokes secure service. And what happens is you have this very long function, extremely long, which basically goes through. There's an enclave call, which we'll talk about a little bit if the operation type is 1. Operation type 2 is the secure call interface, and there's a third one, which is for flushing the TLB. But there's a large switch case, which extracts from the secure call arguments, the secure call to be invoked, and goes through all of them. So secure service create process, secure service initialize process, keep going down. There's some other ones here. get context and set context, which you can't really do unless you are in debug mode in a isolated user mode process or a secure process. One of the ones that I did for Black Hat, let's see if it's down here still, which is and again, there are tons. There's like 270 on this version of the secure kernel that I have. Secure pool, get PEV address as an example for secure processes. If I keep going down, is this the one? No, it's not. There's one for shadow stacks, which are down somewhere lower here. But as you can see there, there are just tons of secure calls here, and they all do various things. Shadow stack assist is one of them. I talked about this in my Black Hat talk. When you create a shadow stack, it goes through here. And again, these secure service are not in the secure kernel symbols. Secure kernel does ship with symbols, but they're very, very limited. Protect kernel data page. This is a feature called KDP, or kernel data protection, in VTL0. It just goes on and on and on and on. So I won't bore you anymore. But basically, that's what happens. Is when that transition happens, the VMCS gets updated and secure kernel enters. It will do this invoke secure service. And there's no thread scheduling in secure kernel in like how there is in VTL0. So what happens is, if it's applicable, which we'll see here in a little bit, something called the secure thread cookie, which is maintained by VTL0, is also passed to the secure kernel. And the secure kernel knows, based on this cookie value, I know I need to go get this thread to perform this secure call in context of this secure call. So here's how something actually gets invoked. So I'll stop sharing now. Shadow stack. Let me just do this for completeness sake. Where was this at? Create NT kernel shadow stack. So this is from my Black Hat talk, and this is down in here. So that's one of the items too, is creating a shadow stack. And what that means, it doesn't actually, like, it does some configuration, but it mainly is to protect it in the slot entry for VTL. So now that we have kind of idea, okay, here's this secure call handler, but how do I get there in the first place? How do I do this? How does this work, so to speak? I will show that right now. And if there's relevant questions, feel free. But for now, I'm going to open up IDA for NT and then open up my project too.
I got that question once too in an interview about optimization of translation look-aside buffers in the hypervisor. That's a tough question because
yeah,
you context switch, you flush them in user mode, but the kernel is different.
Yeah, exactly. Newer processors, and ARM has this too on a lot of them, which there's some performance to be had where you can have multiple TLB entries for the same address because they're tagged by process. So that helps a lot too, where you don't have to flush everything. But yeah, this is systems programming. Like, it's difficult to all this stuff. So I will open up NT.
At VM Probe, your question: what prevents an attacker from patching the secure kernel Hyper-V binaries on disk to disable the mitigation after system restart? I would imagine code signing and such, but Connor, you got something on that?
Yep, code signing, exactly. All of that is completely relevant. All of that's validated. There's a lot of hypervisor validation that goes into. There's some mitigations that can basically say only Microsoft vendor, hypervisor is allowed to load, as an example. Some of this other thing. So let me go ahead and share screen. I'll just go ahead and share the entire screen so I can move my project over to it too. But this is the main brains of the operation. So we are in NT now. Let me go ahead and increase the font size too.
It's good.
Okay. So this is an NT now. So for those who don't know about Windows, it's very easy to tell where a function is or what it does based on the name. So you have here VSL. This is the virtual secure library, like VSM library. P infers private. So this is a private function. And what that means is generally speaking, it's not exported or anything like that. But it contains undocumented functionality and things that, security researchers are probably interested in. So this is enter IUM secure mode. And if you look at cross references to this, these are all of the various secure calls which can happen. And we could see a ton of stuff. Secure pool operations, hot patching, just a ton of stuff, enclave related, system call tables, all of this good stuff you can see. And so you could just keep going back and going back and going back. This is how you reverse engineer how the arguments are passed. So like if I go to shadow stack right now, VSL allocate shadow stack. I've already reverse engineered these, but basically you would just keep going back and going back and going back and going, okay, how does VSL allocate kernel shadow stack get called? And then you need to have this secure call args structure, which I'll show here in a second, which is in the SkBridge project. But basically what happens is this function gets called. This does all of the magic for encapsulating all of the memory as physical memory if it needs to be, packaging it up, making the hypercall, all that good stuff. So what happens is we can just walk through this code together. There's multiple operation types. 2 is secure call for the most part. 3 is flushing the TV, as we talked about. We'll get to this in a little bit, but there's actually an undocumented ETW event which gets emitted that you can enable, which is not enabled by default, which is part of VTL1Mon, which I'll show in a little bit too. In terms of how we can actually view all of this information. So, and then this switch to VSM VTL, which does the hypercall. And again, this is all jacked up because a lot of this is a assembly routine. So what happens is all of the secure call args, which are packaged up, are sent in. So you have the operation type, which gets packaged up. You have the actual secure call or system call code. I haven't even gotten to normal calls, secure system calls, all this other stuff. This is just VTL0 to VTL1. You get the call code, and then you go through, right? Enclave calls, which are designated by operation type 1. This are associated with the secure cookie. Basically, when you create an enclave, that thread is going to have a secure cookie, which denotes what thread to handle that on, which does something really cool, right? If you don't have that mitigation on, I talked about earlier for enclaves, which allows you to isolate so that your enclave in VTL1 cannot access memory in VTL0. If you don't have that on and you do allow the access, you can actually have a local variable on the stack in VTL0 and be able to access that in the enclave, thanks to some of the secure thread cookie, which allows the secure kernel to handle a given call on a particular thread. So there's some other stuff here. Again, this is where secure calls get ETW events as well. And then you have normal calls here, which we'll talk about in a little bit. So as I talked about earlier, there's a lot of system calls which are not fully implemented in the secure kernel. The secure kernel is very small to reduce the attack surface and complexity. But let's say you need to do something like query a thread or query a process or something like that from an enclave or some other place. You have to go back into the normal kernel to allow that system call to happen. It's not all the way true. There are some system calls which are handled all the way in secure kernel. And then there's something called special normal calls, which we'll talk about earlier, which have a little bit of functionality in secure kernel and a little bit of functionality in NT. This is what gets invoked in that case. And you can basically filter on only allowing a certain amount of secure calls to occur. But this is the main operations for this. So why do I bring this up? Why is this relevant? So I'll bring this screen over here now, which is my SkBridge project. And let me zoom in on the text here. Is this big enough or should I zoom in a little more?
Maybe a little
I can
bit
zoom in
more.
more. Okay.
Yeah, perfect.
Okay. So this is my Secure Bridge project, which basically is 2 components. It's a driver and it's a client. Again, this is not a promotion of Connor's SkBridge project. I'm just articulating how I'm able to invoke some of these secure calls manually. So as an example, right, if I go back to here, and I go back to, let's go to, as an example, the shadow stack one. Very good example, actually. And I go to allocate shadow stack, and I go to callers of this, allocate shadow stack pages. Again, this is all in my Black Hat talk. And I go back even more to create stack. Where does create stack happen? Create shadow stack. Where does create shadow stack happen? It happens as a thread is being initialized in a lot of cases. This is happening in line in the kernel, right? So what's cool, I think, about the SkBridge project is there's no way natively to control many of the arguments for this operation. Because what happens is, you provide a value, but then you're relying on the kernel to translate it into physical addresses, all this other stuff. Because again, it's happening in line of something. Whereas in the SkBridge project, you could create shadow stack with user mode addresses or something. You'll crash the machine, sure, because it does some hypervisor wonkiness or whatever. But it allows you to manipulate all of your own calls and do your own testing without basically going, okay, I'll just create a thread, control maybe a few of the parameters for the stacks, and allow the shadow stack creation to occur. So I'll go back to here and I'll go back to SkBridge. So first of all, right off the bat, I have in the client an examples file. This gives you a few examples of secure calls to actually execute itself. So this first one is get secure tab address. So secure processes, which are in isolated user mode in VTL1, their PEBs and their tabs can be retrieved through a secure call interface. So the secure tab, you can actually get the address of it. So there's some nuance here. You have to be secure process. So what this does in this example is it gets the TID, the thread ID of LSA ISO, which is a trustlet which runs in VTL1 for the feature Steven mentioned earlier called Credential Guard. It gets the thread ID of LSA ISO. What I think is very cool about SkBridge is the repeatability aspect. So if you reverse engineer the arguments for get tab, it requires two things. It requires a secure thread cookie and it requires a kthread object itself. Well, you can't do that from user mode. You can't get the secure thread cookie, which is part of the kthread object in Windows. You can't just get that from user mode because you have to read kernel memory for that. You have to dereference something. You're not able to do that. So what I did is I add something called field descriptors to each field, which basically gives like a transformation option. So in this case, it says, hey, take the TID specified in field 1 and convert that to its secure thread cookie, and it'll do that for you in kernel mode. Take the TID and turn it into its kthread object. Then what it does is it looks up the actual secure call value through a map that I have, which is by string. This project as well uses symbols to keep everything very nice, where you don't have all, when you're using undocumented structures, all those offsets change, right? Like the secure thread cookie offset and kthread may change based on Windows version. What this does is for the machine that's running, it will do a one-time init with the driver, give all the offsets which are needed. So you don't have to, hard code all of them. And it also will index this map, which contains all of the strings of the symbols. So if I have the local kernel debugger, which I'll bring up here for a second, I go to local kernel debugging. I can do DT, NT, SK service. These are all of the secure calls, which are in the symbols. So it uses this to allow you to do that. And this machine I'm running on runs on a Canary build of Windows Insider Preview. So some of these may not be available to on your machines. So it gets a secure fault value and it just does the wrapper call. And the wrapper call simply just does an ioctal invocation, passing in all the data and returns it. So now I'll show you what the driver does, and then I'll actually execute it on the machine. So the driver, it's actually right here. It works just through this ioctal handler. So this ioctal handler basically gets all of the input that's passed. And there's basically two ioctals. There's invoke secure call, and there's the one-time init, which basically has an array of all of the known offsets for all of the undocumented structures which are being used like kthread and whatnot. So there's the one-time initialization, but the secure call interface goes right here. So what it does is it translates all of the bridge data to secure call parameters. So as I talked about, there's a level of transformation that needs to be done, turning a thread ID into a secure thread cookie, as an example, some of those things. It goes through and it performs all of the translation. And what it can also do is it can queue an APC to a particular thread if you need to actually invoke the secure call in context of one of those IUM threads. You can do that as well, which is one of the features. So it goes through and then it makes the secure call by just invoking the private function itself with 2, which is the type. And then it passes in secure call type as well, and then the actual arguments. And again, there's this whole level of translation which can be done too. So one last thing that I'll show is all of the various descriptor options, and I'll talk about some of the patterns. So it can encapsulate a parameter as an MDL. This is a very common pattern with talking with hypervisors, because MDLs can lock memory in physical memory, can lock memory into physical memory, right? So when you're talking to the hypervisor, it doesn't necessarily have access to the virtual address space directly. So you can pass parameters of physical addresses so that the secure kernel, as an example, can map the memory, or the hypervisor, or what have you. So that's a common pattern you'll see in some of the secure calls. Shadow stack is one of them. You pass in the page, the page frame number of some shadow stacks as well, and they have some MDL encapsulation. PID to process object. So you basically provide a PID and say, actually use the process object, the eProcess. You have something called secure handle, secure process handle as well. So if I come to local kernel debugger, and I just take dx cur process dot kernel object dot PCB, which is the K thread, dot secure state, and I just do secure handle, it's not going to have anything. It's going to have 0. But if I do dx for the cur session processes, show me processes where p dot kernel object dot PCB dot secure state dot secure handle doesn't equal 0. And we have a few of them. These are all processes which are technically secure processes in the secure kernel. This secure handle, we then can select on. We could say, for those processes, show me PCB, which is the secure state, secure handle. Show me the secure handle. So these are just like handles in traditional NT, except secure handles normally are prefixed with this 14 in the upper nibble of the D word. I think this is D word. Oh, 64, even though it's only 1, 2, 3, 4. Okay, it's 32 bits, but it's a 64 data type in the symbols. And so what happens is in the secure kernel, there is actually a function to open an object based on its handle. So VTL0 says, hey, here's the process that I need you to operate on. Secure kernel has all these different object types, just like NT. One of them is secure processes, which is represented by the undocumented SK process structure. And this is how it gets that information. So you can't access this stuff normally. You'd have to just read kernel memory, keep dereferencing. That's one of the things that this project can do. If you need a secure process handle, which is you need it for some secure calls, you can just say, hey, for this PID, use the secure process handle. Thread object and then thread cookie, which is what we talked about earlier. PID to section object. There are some special secure calls that I reverse engineered where basically you need the section object for a process or an image. This can allow you to do that. Secure image handle as well. Secure image handle basically is the same. It's a type of object which represents like a loaded driver or something else. Kernel image based to secure handle as well. Again, drivers are associated with secure images. Then you have some of your physical memory primitives. Virtual address, you need to convert that to a page frame number. Some of the operations require that. So this allows you to say, hey, I'm specifying your virtual address, but when you do the secure call, make sure it's its page frame number. And then also there's dynamic. A very common pattern is basically having an MDL as one of the values, and then each of the subsequent parameters are the page frame numbers described by that MDL. this allows you to do that. And then there's a reserved option, which gets cleared out every time a secure call happens and is only set by the driver itself. So now we can go over to this VM over here. So I will let me turn this off for a second. I think I already created the service. Okay, I created it already. So basically, users, anon, desktop, SkBridge. This contains everything here. This is a live demo, so it could crash. But basically, it's going to go through and do all of those secure calls which occurred. So it did a secure call, and it got the secure TEB address for LSA ISO, which is here. The secure PEB, it got it from here. There are what's known as secure allocations, which I realized I glossed over in the examples. A secure allocation is used a lot of time by SKCI, which is the Secure Kernel Code Integrity Library, but it's a secure call that can be made. So there's create secure allocation and fill secure allocation. So in this example, right, I allocated some memory and I set it to all 41s as an example. And I say the size, which is required by the secure call. I get the value and I do the invocation. So this does the create secure allocation. And then there's a fill operation as well. So the fill operation requires the previously allocated secure allocation handle. So again, there's an object for secure allocations, which you can see here contains that 14 up here in the bits. This is the secure allocation handle that represents this allocation which exists. So basically say, hey, here's the allocation handle. Here's the offset in the allocation I want to write into. And then you have to have an MDL which describes the allocation. So that's what I do here. In this field, I say, here's the allocation value. Here's the MDL size. And I need you to encapsulate this parameter as an MDL. What this then does is it instructs the driver to make argument 4, which is this argument, the PFN of argument 3. So what this does is say, hey, for field 3, get the PFN for the MDL, which again, this is just this common pattern that you see in the secure kernel and why I put all of this in this project for these weird, well, not weird, they're common cases, but just situations where otherwise you have to recompile your driver, do all of this stuff. And it makes the call. So in this case, there's now a secure allocation in the secure kernel that's filled with 41, 41, 41, 41. Now, I know what everyone's thinking. Okay, I'm going to go make secure calls and try to fuzz this thing and get this weird offset. Secure kernel has very powerful primitives. It can map the entire MDL into the secure kernel. It can then validate the field. So it can go, hey, I see that this MDL says it's only 36 bytes in the MDL, but you provided 1,000 bytes as an example. That's not going to fly. It does all of this very, very good validation. And then it does a lot of validation itself on the allocations. So that's the secure call interface in a nutshell. And this project will allow you to. Now you need VBS enabled and you need HVCI enabled as well. So does anybody have any questions? Because now I want to very quickly move on to normal calls, which is the reverse back and enclave calls. But if there's any questions about secure calls in general, please go ahead and let me know.
Couple questions, trying to see which ones are relative to what you're talking about.
And if there's not, no worries.
It's a bit of a long one. Do you think that secure services can allow dumping processes in VTL1, for example, LSA ISO, through secure services such as secure service debug process?
Yeah, no, because, well, I mean, it's possible. Yes, the options are there. You have to configure your secure process to enable debugging for those secure calls to even work in the first place. So LSA ISO is a production executable. It's not going to enable debugging by default. And so you're not going to be able to invoke those. Well, you can invoke them. You'll just get an error or it just won't work because they haven't enabled debugging themselves. VSLP enter IUM secure mode is not exported by NT. Is it CFG compatible? Can it be invoked in context of a kernel arbitrary code execution vulnerability? This function is not a CFG target because it is not invoked indirectly anywhere. It's invoked just directly. It's in the NT kernel itself. I'm trying to remember if I had issues with this before. if I had to compile. But I have HVCI on, which automatically turns on secure. Oh, you know what? I actually do think I had. No, it's when I tried to invoke it. Yeah. So you are right. So completely ignore what I just said. In the secure kernel itself, it's not a valid call target. It's not in there because it's not used in an indirect call. So I disabled CFG in this driver in order to allow that to execute. I just didn't compile with CFG support. So you are right. I mixed up my words there. It is not a valid call target because it's not used in an indirect call. And I guess really quickly, before I move on to that, go ahead if you have one.
I was going to say real quick, this one might be something you're covering, but how does the secure kernel validate the integrity and structure of parameter buffers passed from VTL0?
Yep. So I have a blog on this. It's about secure images. So I can, I'll share it, Steve, to you. It's called Dissecting Secure Images. I'll share it in this chat, and maybe someone can put it in the YouTube chat or where have you. But basically, it goes over all of this, and it has to do with what I talked about earlier. So a lot of these parameters are packaged up as MDLs. The secure kernel does not operate on that MDL. Everything gets mapped into a temporary space, usually hyperspace or somewhere else in secure kernel. All of the validation is done to say, okay, these parameters are valid, this MDL is valid, yada, 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 yada. And then it gets remapped into secure kernel. So you're not even using the NT copy. You're using, a local copy to the secure kernel itself. My blog goes over that, and SAR's talk that I mentioned earlier goes over some of the validation that occurs as well in VTL1. But like the secure call interface, like I know people like to laugh and Microsoft this and that. It's actually pretty good. There's been vulnerabilities in it, but it's pretty good on validation and whatnot. So I will go ahead and close SkBridge. And what I will quickly open is VTL1Mon while we're on the subject, and then I'll move to normal calls. I won't spend much time on this because it's just an ETW interface. I just want to show why it could be interesting. So basically, this is just a user mode application that just accepts a path to a CSV file that gets created. And basically, it configures an ETW trace, which again, this is just, all of the standard stuff you need for creating ETW. And it also enables stack traces for this. I enabled as well. And then it starts the configure. No, I want to go to enable VTL1. So here's kind of the part is this mask of performance events is actually undocumented. So it's documented now in this project, which is on my GitHub. And basically what you have to do is you enable performance events for VTL changes. But what's interesting is this comes in the thread provider in ETW, which is interesting because a lot of these come through a dedicated performance GUID, but this one comes in through the thread GUID for whatever reason. And what I'll show you, so I documented that. And then I documented also ETW call. Let me go to callback.hpp. I documented the opcodes, and I also documented the system call event data, which is not documented as well. So all of this is now documented. And let me show you how this works real fast. So this is very easy. You just go to VTL1Mon, go to x64, go to debug, and then VTL1Mon. So what I'll do is out.csv. Just press enter. So then I'll go over here. So there are secure calls that are going to be happening in the background. Don't get me wrong, but I'll just go over here and users, anon, desktop, cd, SkBridge, dir, cd build, dir, SkBridge client. So we have a few more, and then you just press enter to terminate the trace. It saw 231 events. So no one get upset with me, but I have open office on this machine that I just dedicated for this to actually open up the CSV file. So you just come here, out. Okay. And basically, let me zoom in a little more. It just has timestamps, raw timestamps, and then the actual secure service, which was called. You can see some of these here. secure allocation. This is from my process that I did. It contains the TID and the PID, which actually did these. There are some secure calls which are always made like periodic, which is just like a check-in. Flushing primitives. You'll see a lot of page validation as well. I only ran this for a couple of seconds, but you can get a list of all of the secure calls that were made. But what I think is cool is I added symbol functionality here and the call stacks. So I can take this whole thing and actually view the call stack that led up to the secure call being made. So in this case, the kernel called mi flush TB list, which then called HVL flush range list, which called VSL flash fast flush secure range list, which then entered secure mode. So you have all of the call stacks which led up to this. Now, if I go to mine, it's not going to have symbols because I don't have public symbols on here. But it will show you the offset in the binary that made the call. So SkBridge, client, client. So yeah, that's VTL1Mon in a nutshell. You can actually view these secure calls for your own purposes. So I'll stop talking about this now and go to normal calls. So what you can do is, I like to use WinBag a lot to open as a dump file the secure kernel. So it gives you this familiar, kind of introspection into secure kernel, but you can use, the WinBag queries and whatnot in here. So in this case, there's no you can't step through. There's no debugger. There's no, anything like that. Everything is just 0, 0, 0, 0, 0, 0. But what I want to talk about now is normal calls. So again, as I talked about, we have situations where secure kernel needs to make a system call to query a process or do something like that. Most of the time, that is going to result in a call back into NT. And that call into NT, which we saw earlier, comes through VSL dispatch IUM syscall. So how does this work? So what happens is, let me actually open secure kernel. And let me go to here. Here's the best place to do it, actually. So compact service table. So what happens is at startup, we have to basically compile on the fly the system call table. So this IUMP, which again, isolated user mode private function, gets called. And what happens is there is a descriptor of all of the system calls. So if I go to the debugger and I just do DPS, I do, move this up, secure kernel, descriptor. These are all of the descriptors in there, 32 bits each, that give information about all of the system calls which exist. So what happens is for the maximum, so the maximum system call number that's provided, the descriptor, which is hard coded in the binary, gets pulled out. And I did some reverse engineering here to figure out, okay, what do all these mean? So as far as I can tell, 1000 means that the call is enabled. Not all system calls are enabled. So even though all system calls are there, not all of them are enabled in the secure kernel. And if you try to invoke one that's not enabled, you'll just get an NT status error. And what happens is all of these get inserted into the dispatch table. So all of the entries in the dispatch table contain the offset to this IUM generic syscall, which is a function, which does SkSyscall. And what SkSyscall does is it compiles a secure call argument structure, and then it eventually ends up through a normal call in the VSLP enter IUM secure mode, which then calls the dispatch function. So by default, every single system call has the offset to the generic system call function from the table itself inserted into the dispatch table. So that's done for all of them. So all the calls get fixed up. But then there are special calls. So I've seen some people talking about this before online, a little bit in some cases. this disp entries is not all of the system calls in the secure kernel. What happens is for what's known as special calls, so calls which first need to execute in secure kernel for normal calls, but then eventually go into NT or maybe don't go in NT at all, they get fixed up with the function in the secure kernel, which is responsible for handling the system calls. So by default, all system calls that happen in secure kernel that need to go into NT are going to go through this generic system call, except for these special ones. And these are also hard-coded in the binary. So again, if I do DPS secure kernel, I come here. These are the special system calls, and these are the system call numbers. So wait for single object is special. Release semaphore is special. Set information thread is special. Allocate virtual memory is special. And these are the system call numbers. So these get patched up in the dispatch table. So the dispatch table then contains basically all of the entries contain offsets into generic system call except the special ones. And they get fixed up to call their respective entry points, which would be all of these here in the disp entries. So that's how everything gets fixed up. Right. But then let's do a cross-reference to when a system call actually happens. So a system call happens, syscall happens. So again, secure kernel or isolated user mode does a system call, which goes down into the secure kernel or goes into NT or whatever. Eventually we'll go into NT, excuse me, comes here. So we get the associated descriptor. And this is just some of the reverse engineering that I've done here. So what happens is the descriptor contains a few things. One of the things that the descriptor contains is an offset into the IUM syscall arg descriptor, which contains a pointer to like how many arguments or like, let me show you, arg descriptor. Then there is a, not a custom API. There is it in here? No, it's not in here. Where is it at? Oh, it's actually in here because the index is used. It's in this NT generic call. NT generic call is the one that handles them. There's a argument function table, which contains these various helper functions for the various data types that are being used. So this does some sanitization of this type, this type, this type, this type, right? How do we know which one to use? That comes from the arg descriptor. And how do we know which index to use in the arg descriptor? That comes from the descriptor itself, from the original system call descriptors, right? So we know how to get the arguments. We know how to get the number of arguments. So part of the descriptor as well as the number of arguments that are actually being used. And so what happens is once that gets used, this call into NT generic happens. You don't have to go into NT generic. There's a custom system call that exists, custom API. As far as I can tell, there's only one in there right now, which is this trace event system call, which is like a custom one. And so what I've done is there's more to it than this, which we'll see like in enclaves. These descriptors, some of these descriptors are used to determine like, can an enclave make this system call? Are kernel pointers allowed? Some of this various things, which I'll show here in a second. So coming back to here, I have this winbag script, winbag command, which I wrote. And basically what it does is based on all of the reverse engineering that I've done, and I'll walk through this command, it tells all of the information about the normal calls, basically. So system call number 1, it has one argument. The index into the arguments table is this. No kernel mode pointers are allowed, and it's not allowed to be called in an enclave. Number 10, as an example, it's got 3 arguments. The index into the arguments table is this. Kernel mode pointers are not allowed, and it's not allowed in an enclave. But some calls are allowed in an enclave. So system call number 13 has 4 arguments, and it's allowed to be invoked in an enclave, which I'll talk about in a little bit as well. So what this command does is it creates an array of a very large number, and I learned this from my friend Jordan Shafir. There's a winbag issue where you can't give a dynamic, well, it's not an issue because it's the same thing in C. this needs to be a static value. So what we do is we provide a very large array, then we take from the array. So we say whittle down the array actually to only show what's in syscall descriptor limit, which is the top system call number that can be made. And then what happens is I parse out all the entries. So is the system call enabled as an example? How many arguments does it have using this bit mask shift? What's the index? Are kernel mode pointers allowed? This is the mask for kernel mode pointers. Are these allowed in an enclave? This is the mask for an enclave call as well. And so you can see which ones are allowed in enclaves. Enclaves have a reduced system call interface, even more so than the regular normal calls. So this is all the information that is here. Again, this will only work in the secure kernel, right? So that is how the secure call interface, the normal call interface works. So like, let's take an example, NT query system information. It's not called anywhere because it's a system call, right? This is one of those special normal calls. So as you can see, if I scroll down all the way, eventually there is a call to, let's see where it's at, NK query system information, which is going to do the generic system call. But look at how much code there is before here. There's a lot of handling that goes into this, which I reverse engineered back. So any system call that happens to NT query system information does not automatically go into NT. It first goes into the secure kernel version, NT query system information. And we go through. So like secure kernel also doesn't use the traditional KPCR, like the control register or the processor control region, excuse me, or K-thread or whatever. It has its own secure kernel versions. So I only know this because I've done it enough. Some of these offsets, but basically flags. There's a flags here associated with the thread or process, and 200 hex is an enclave. So as an example, enclaves can only use system emulation basic or basic information on x64 systems. Some things are different on ARM. So you can see how there's this real granular control for system calls that goes back into NT. We don't just arbitrarily let these kind of sensitive functions go back. We first do a lot of validation in the secure kernel before we even go back. And some of them may not even go back at all. As an example, if the secure kernel needs to get secure boot information, it's going to go to this function, which does all of the information for you and returns back, and then is going to exit. Like this is the exit label. It never even goes into the regular NT kernel. Or firmware table information, that doesn't go in the NT kernel. Processor information, that does not go in the NT kernel. It stays here. But on top of that, there's a lot of other things too. Like NT query information thread is a very interesting one too. So NT query information thread, let me see where it's at. So for enclaves, you can make a call to NT query information. So this is the, let me see if I have it here. Thread basic. No, I don't have it here. Let me pull it. Thread basic information. So I'm just going to take this for a second and add some types in here real fast. Long. Then let me add, I'm off screen if anyone's like, what is going on right now? So I can show you some of the interesting things that the secure kernel can do. So let me take this client ID, add type, just do void, client ID, and then we'll just make everything else pointers, add type. Let's just call this long. Let's just call this a void pointer. Affinity, I think, is just an unsigned long. I think this is an unsigned long too. See if this might be an epic fail. No, let me add it in. Okay. So if I come back to here, this I know is the thread basic information structure. Thread basic information. Or is this a pointer? I think it's a pointer. Thread basic information. Yes. So something that's very interesting here. If you call NT query information thread with basic information class, this is an allowed call. You're allowed to do this. But what happens is after the call to the kernel is made, so we call the regular NT kernel. First of all, there's some sanitization functions which exist for, or is it sanitized? Yeah, private and most of them, that for some of these dangerous system calls that can be made, there's some sanitization. So one of the things a special normal call can do is not only just implement half the call in secure kernel, it can completely transform the output. I was doing this in an enclave before, and I'm like, why the heck can I not get the process ID of the process housing my enclave, which you should not be able to do anyway because you shouldn't trust it. And the enclave documentation said you're not allowed to basically know anything about the process which loads your enclave because any process can load your enclave. But it was just junk information. And that's because even though this came back correctly from secure kernel, from the regular kernel, like it had a valid process, it gets overwritten with data from the secure kernel, which is the information from the secure process structure, as an example, or the secure thread structure. So secure kernel has tons of granular control on this. So now what I'll do, if there's questions on any of this with normal calls, this basically just does the transition to VTL0. It compiles everything as a secure call arguments, and then any data that's returned back occurs as well. But what I'm going to do now is I'm going to share my test enclave I wrote for this, for these purposes. Let's close this for now because this machine doesn't have much in the way of RAM. So let's close
Put this question
down.
up. So if I send secure service debug process to SK from a driver, I can debug a VTL1 process? Is it the sole requirement?
No. And the reason why is because a given process, a secure process, has to be enabled to do debugging. So just by default, no, you're not going to be able to. You need to do it on a secure process which enables debugging, which you're really not going to find, especially on a native Windows machine. So what I have is we did VTL1Mon. Let me share very quickly. Stop sharing this. Let me share my, and I'm almost done, I promise. I know I'm belaboring everything. So screen one, come down here. Okay, and I'm just going to do a quick little whiteboard very, very quickly on VTL0, VTL1, enclave.dll, enclave host exe. All right, I think it's sharing my screen. I'm not sure if it's caught up on the stream side. Oh, there we go. Perfect. Okay, so for those who don't know, VBS enclaves are something which enclaves have been around for a while. You have the traditional ones associated with Intel and TPMs and that sort of thing. But now we have VBS enclave. So we can use VBS in order to protect data. What's really, really awesome is that Microsoft in the last 10 months or so, maybe it's a year, maybe it's a little more, I can't remember, allows third-party developers to create VBS enclaves. So a third-party developer can make their own enclave, but it's basically a DLL that gets loaded in VTL1 that's a part of a host process. So what's really cool about this is, let's say I have driver vuln drive.sys. This is in kernel mode of VTL0. Who thinks that vuln drive.sys can directly access memory of enclave.dll? Probably some people think you can because kernel mode and user mode, but we can't because they're in separate VTLs. So even an attacker with kernel mode privileges in VTL0 cannot compromise the integrity of this enclave in terms of manipulating its memory directly and all of that good stuff. So what happens is there's also something called enclave calls, where Enclaves are allowed to invoke the services of each other. So the host process, which creates the enclave, and I'll show all the APIs and all that stuff, creates the enclave. It's basically a region of memory in VTL1 that you can load DLLs in, which are called enclaves. They're really enclave DLLs or images, and the enclave host itself is just the host process. But the enclave is just a region of memory that you control, that you can load DLLs, various DLLs, and that are compiled in a certain way, have certain characteristics on them, and do certain things. And these enclave calls can happen where a host can invoke a function. You can think of it almost like RPC a little bit. Hosts can invoke a function in VTL1, and then VTL1 can actually invoke functions in VTL0 itself too, which is really cool because you can store secrets. You can do all kinds of interesting stuff by storing information in an enclave itself. And so what I'm going to do is I'm going to show a demo VBS enclave because I want to show a little bit about how enclave calls work just at a high level, but I want to show the system call filtering stuff, which I just mentioned. So I'm going to open up over here the enclave, and this is the last thing that I have. Share screen. I can go to entire screen 3. Okay. Hopefully everyone can see this.
Yep.
Basically, there's two things here. There's a main image, which is the DLL, and there's the host. The host is responsible for doing all of the setup. You have to call a few functions, create enclave, which actually creates the enclave itself. You specify the process because technically speaking, every process object has an enclave table, which I'm guessing, I haven't looked into it very much, but I'm guessing you could have multiple enclaves in a given process. Create enclave, size, all this stuff. Then you actually load an image into the enclave, then initialize the enclave, and then you can make an enclave call. All of these do secure calls. So they're not here, but this is a secure call. This is a secure call. This is a secure call. If I open up in here, let's go to NT. Oh, actually, I don't want NT. I want secure kernel. Okay. So if I go to IUMP, create enclave, SKMM, create enclave. These are all done via secure call. So you can see which fields are going to go into which arguments. Field 2, generally speaking, is used as the output parameter that's passed back for optional output on a secure service call, but that's not necessarily always the case. So you have create, load enclave, initialize. Well, what do we have here? Create, load, initialize. So those are done via secure calls. But then you can actually call enclave functions. So in this case, what you do is using the address of the enclave, which is returned by create enclave, you call get proc address on the function you want to invoke. So any function that you want to invoke has to be exported with C linkage in the enclave DLL. Technically speaking, C is the only supported language, but Microsoft has some good examples with Rust and C++. So I want to share this enclave. Steve, I'll share this in the chat because it's a very good blog about security patterns, and a lot of people may have missed this blog before. It's a very good blog, in my opinion, on things with enclaves, so new mitigations, which basically, like I said earlier, an enclave by default can even access the local stack of the housing process which created the enclave. There's mitigations to turn that off, to say VTL1 is no longer allowed to access VTL0. There's a lot of things you have to do, not necessarily probing how we do in kernel mode, but you need to validate some things like the memory you're accessing is in a certain VTL or things such as that. But you can use this call enclave function to actually call the enclave, and then this is the output parameter, and you can also pass in data to it. So I have in here DLL main. Enclaves need a config. So this needs external C linkage as well, because the loader actually looks for this. It has to be named enclave config like this as well. And this has all the information that you need. Again, there's a whole development guide as well let me do VBS Enclave Dev Guide. I'll send this as well, Steve. Sorry, I should have prepared this before. That basically will tell you what you need to start developing an enclave, all that stuff. What's very cool is you can enable debugging on this. So someone was asking earlier, well, how do I debug some of this stuff? What's very cool is you can enable debugging on VBS enclaves where you can actually break into the debugger while you're executing code in your enclave, which is very useful. Obviously, you wouldn't want to put that in production, but the way you would do that is you have a flag here. It's debuggable. So basically, I have DLL main, which does nothing, but I have one exported function called demo function. And it's going to have a breakpoint here. And basically, it tries to show invoking system calls. So I have a systemcalls.asm. Another thing as well, sorry, I'm going to send another link in here. VTL available APIs. One thing that's very cool about enclaves is that Microsoft only documents a few functions which are available through VirtDLL, which is basically like an NTDLL style, because NTDLL is also mapped in Enclave, but NTDLL style, which contains some basic functionality for enclaves. By default, the virtdll.lib, the static library on disk that comes with the Windows SDK, won't link to many system calls. So the documentation says you can only make, a handful of system calls, but it's actually not true. VirtDLL exports a bunch of system calls, which technically are not documented by Microsoft that you can call. And all you have to do in this example is just do a direct system call where you can basically say, what's the system call number I want to invoke? Or if the function is exported itself, a lot of these system calls which you can invoke are exported. But on top of that, this is where this comes into use, is allowed enclave. So in this case, if I remove everything here and I only want anything which is allowed by an enclave, select where equals true. And that's not going to come up as a grid if I had to guess. No, it does come up as a grid. So here's all of the system calls which are available to us in an enclave on this version of Windows. Now you have to map these over. But as you can see, 36 hex is 54 decimal, which is right here. That's one of the ones that's allowed, which is protect information. 36 hex is query system information, which if I take this and I go to 36, this is 54, or I already did that one, didn't I? I'm very dumb. 50 is the other one, which is protect virtual memory. Formats 0x50. So 80 is also here as well, allowed by an enclave. So you have other system calls which are not even documented that are allowed that you can actually call still either by get proc address or by just doing the system call directly, which is what I've done here. And so if we come to was it the NT that I had it on? I hope I didn't close this tab. I felt like I had a lot. So enclave calls are in here. I had a whole thing, where was all that enclave stuff? RTL call. No. Oh, I think it was in Secure Kernel. Okay. No, it was this one, I think. Did I document all this? Prepare enclave call. All my progress went away. But basically what happens is the enclave will prepare a stack frame with RTL call enclave return on the stack. And so why that happens is when the enclave call completes, it does another call back into VTL0 after the call is completed to return to it. And that's what this does here. I messed up, but some of the stuff that's in here was that. I thought I saved that progress. I guess I didn't. Do I have it back here at all? No, I didn't. Okay, anyways, that's fine. So I will close this. Let me attach my. So I'm going to have two debuggers here. I'm going to close this one first. So this is on the outside, which is my network debugger, which is debugging the VM. And then this is my debugger on the inside for my enclave. So I'm going to attach the enclave. So I have debugging enabled here. So if I press go, I have a breakpoint in my enclave itself. So execution is right here. So we are in the enclave. So if I hit K on the stack inside the VM, you can see the stack here. This is because when this function returns eventually, this was set up by the secure kernel in normal cases. If I fully unassemble this, what it will do is fix the stack back up and then do a call enclave as well. Again, call enclave can go both ways, VTL0 to VTL1 and VTL1 to VTL0. So coming back to system calls here. So this first call to NT query system information, 0x3e, which is emulation basic information. So we know an enclave should be allowed to make this call. So if we go and we do RAX, it's successful. And then if we do DX, our system basic information, we have the information here about the system, max user address, all this stuff. So to demonstrate this even more, now I'm in the kernel debugger. I'm going to set a breakpoint. VSL IUM, or it's VSLP dispatch. Yeah, here we go. On this dispatch function. Where'd my VM go? Okay, my VM's right here. So I'm now making another call to NT query system information, which we know we should be able to make based on our analysis earlier. So I come through here, I come through here, I come through here, and then I go to syscall. I press T, and oh, my. Hold on, I think that was bad. Enter. Let me get the name of this again. Sometimes with these functions, the debugger gets really weird on me when I set, like if I set a normal breakpoint on enter IUM secure mode, my machine crashes. I have to set a hardware breakpoint. Copy. Oh, this was hit, but it was probably hit by, or okay. So let's try the last system call to NT query system information. Now this class should not be allowed because it is processor information. So we should get an error here. Why is that letting me go through? I tested this breakpoint before. This is making a liar out of me. Let's do cur process.
The demo gods finally woke up.
I know. Contains demo. Dispatch. Oh, I meant W, not 2. No, let's clear that for now. And let's press and go. I tested this before and I'm like, oh, you know, this will look good. But anyways, let's see if the call went through. And it didn't. And it failed with this error, which in WinBag, sorry, I should have been zoomed in here. Error is specified information class is not valid. And the reason being is, again, if we go back to secure kernel and we go to query system information, if we are an enclave and it's not emulation or basic, that's what gets returned. So secure kernel can do some additional, let's see if this works. So last time I hit on the system call, well, let me set the breakpoint now. There we go. I just needed the name. I'm telling you, there's some weird stuff with some of these breakpoints before. So like if I reload, told you I was not lying. I knew that this would be there. So this is my cur process.name demo VBS enclave host. So this is what happens when a legitimate system call that's allowed to occur goes back into the NT kernel. So what happens is you can see our call stack, which still has RTL call enclave return as an example. And we are now in VTL 0. And when we did the system call, remember, it compiles a secure call arg structure, goes back into VTL 0, which then calls into enter IUM secure mode. And it knows, oh, I'm doing a system call. First parameter is the handler, which in this case is NT query system information. And so if we come back here, this is exactly what happens. The system call code, which gets compiled, because again, the secure kernel compiles this, will set in this field the system call number. And it will pass the actual field itself as well. And so the output is also returned in field 1 in this case. So in this case, this is just going to call NT query system information with the specified class and all of that, which I talked about before. So that is there's a lot more nuance with enclaves, like how they work and whatnot. But the point is not to show that; it's just to show the communication between both of them. But an enclave call is a special one that when VTL 0 makes, it will go through this dispatch function as I talked about, but the operation type is 1 for enclave. So for enclave, it gets operated on here. Trying to see if there's anywhere else where it gets. Yep, 1. Sometimes you may not need, like the current thread secure cookie could get updated by the system call, like what it provides, and then later there's a cleanup of the thread cookie to switch it back to what it was originally. So 1 is enclave call. And so, yeah, that's that. One thing I didn't touch on yet is secure system calls. So I wanted to do that real quick, and it's very simple. Secure system calls are ones that are made from VTL1 user mode software to VTL1 kernel mode. So all it does is a ring level switch or exception level switch on ARM, if applicable. And all of these system calls can never be made from VTL 0. And I'll show you why. If you go to IUM.dll has most of them, but VirtDLL has a few of them. If you go to like IUM crypto or IUM copy enclave memory as an example, which can copy memory in and out of an enclave, the system call has 8 here, 8000019. So one thing that I didn't show is one of the things that also gets compacted, compact service table in the startup, is the secure system call table also. It has its own argument table, service table, and it does the same thing. It goes through and it fixes up the secure system call table. Because what actually happens is if you go to, did I preserve it here? I did. Okay, this one at least I preserved. This is the system call handler in secure kernel. So when the system call comes in, a test happens. And it says, hey, determine if this system call is a normal call or a secure system call. If this is set, this upper bit, we know it's a secure system call. And then we use the secure service table and limit. But if it's not, we go to handle normal call, which again uses the patched up IUM syscall dispatch table. So again, secure kernel can make calls into NT, but then enclaves can make even less calls than regular secure kernel software. So I'm trying to think. That is pretty much all I had in terms of presentations. I know I've been going on for a while. If there are questions now, I'm happy to answer them. But if there's anything that wasn't clear or anything that I can sum up, that's the gist of it. Basically, here's how VTLs can communicate with one another. And I have a project for you all, SkBridge, which I want to turn into a fuzzer one day. I think would be cool. because basically it's a nice harness for all of the interfaces that you need, all of those parameter descriptors, which we talked about earlier. So yeah.
Awesome. Thank you. Yeah, this is great because I think there's probably little to no, presentations or information about this being explained so well and demonstrated online. So definitely awesome stuff for those who understand and need it. Yeah, I'm going to go back through some of them. There's a few questions. One of them that popped up was this guy right here. I think we talked a little bit about this before we started, but have you seen much malware research or use of enclaves?
I have. So I'm not aware of any third-party enclaves, but what I have seen is a version of the Microsoft Edge enclave was vulnerable at one point, which is where this mitigation came out of, which is the restrict address space for enclave mitigation. But basically what could happen is there was arbitrary write into VTL1 memory. I think it was just user mode, but it was still an arbitrary write. So what I have seen is that function, that enclave exposes two functions, seal settings and unseal settings. Settings referring to, I guess, edge settings. So what I saw some malware researchers doing was basically taking like a beacon shellcode or whatever, and instead of keeping it around in memory, like it's not executing, but they sent it to the enclave, and until they needed it, then they pulled it from the enclave using that interface. Because again, with enclaves, like if I have an enclave.dll, any process can load enclave.dll. That's why Microsoft doesn't let anybody know basically, or it's not even possible in some instances because it can't be trusted, what process actually loaded you. And so like, let's say I have an enclave which generates a signing key. Like as soon as the DLL main enters, it generates a signing key. That signing key is going to be different in every process because, you know, one memory in one process is not reflected into another. But that doesn't mean if that enclave exposes an interface, you can't ask the enclave to do something on your behalf with signing stuff. So that's the main thing that I've seen. I've seen a CVE, which was a sign that Google had. That enclave is called prefs enclave.dll, I think for Edge. I can send, yeah, here we go. I will send a link, Steve, to the GitHub advisory from Google, where they give a whole POC on an arbitrary write primitive. Enclaves have to be aware of that. Like there's two things, right? There's using it for research purposes, like hiding stuff from, you know, whatever. And then there's using it like, are there vulnerabilities? This is more of a vulnerability thing, but I have seen, like I said, people using it to hide shellcode, etc. But like I said, enclaves, like getting code execution in VTL1 and user mode is like, that doesn't get you anything. You don't have the same privileges as kernel mode. It's not like VTL1 isolated user mode is more privileged than user mode in VTL0. In fact, it gets you less because you don't even have networking. You don't have file IO. You don't have registry. Like you don't have all this other stuff. It's a cool from like research perspective, but it doesn't really get you much.
Yeah, and I think, like I said earlier, you know, memory acquisition tools, I don't believe that they're capable by default of getting that memory. So maybe it's just more of a, you know, you can't find me kind of thing.
Yeah, exactly.
This guy here, do you have any info on what secure services? I'll let you read because that's some.
Yeah, so I tried to look into this at one point and I stopped doing it. And I think what this is there's a lot of functionality for crash dump purposes. I think a lot of it is when a system is crashing and you need to get the dump of a particular process. But don't quote me on that. But I know that those calls exist. I just haven't gone into them much. But again, like that capture process one that you're talking about. One thing that I vividly remember, you don't just call that API. You have to call you don't call that secure call directly. You have to call like 5 other calls before. There's like prepare kernel for live dump, prepare process for live dump. And then there's like all these secure calls that you have to make. So you'd have to go back, reverse engineer all the arguments. But then, like I said, there could be things in there that's like, if it's not debug mode enabled, it's not going to let you. I just never fully explored it. But yeah, I'm aware of it.
Nice. Yeah, we had a presentation recently on actually analyzing and using crash logs to find just interesting data that might be helpful for exploitation and such.
Nice.
Let's see here. I don't remember if I asked this one already. Let me know if I did. So when using SkBridge to issue arbitrary secure calls, how does the system prevent unintended state corruption inside VTL1 if parameters are incorrect?
So that's, again, that goes back to the whole thing. Secure kernel has to be diligent in validating a lot. There's a lot of one-time initialization in the secure kernel where like once a secure call has been made to say like the system has been initialized to this, you can't re-invoke it or something like that. So state corruption in that regard. But there absolutely are things like, you got to remember, Oh, okay. I didn't show this. I meant to show this. Dang it. In the secure kernel. So, okay, you guys want to know a funny story? I was on a plane one time coming back from Black Hat, I think, actually. This is when SkBridge started, and I was doing all this stuff. And I had the original bones of it, and I just did a for loop over, 0 to 200. And I got all these secure kernel crashes. And I'm like, oh my gosh, like I'm going to get back home. I'm going to make all these blogs. Like, it's going to be so awesome. Secure kernel literally blue screens by design in most cases. If you provide a value that's not a valid secure call number, literally it bug checks itself on purpose. So just crashing secure kernel is not a security vulnerability at all. It basically is DOS by design for any of that state corruption and anything like that. So I hope that helps answer your question a little bit more too, that even in those cases where it does happen, Microsoft doesn't care because, again, even if you just, like, if the max number is 255 for secure calls and you do 256, blue screen. And I didn't know it at the time because I wasn't looking to disassemble like, oh, I've got like, dozens and dozens of crashes. Am I just sending 41s into secure kernel? No, it wasn't the case at all.
Wasn't there some blogging going on from Microsoft recently, or in the last few months, about no more blue screens, kind of like triaging and handling the crash and recovering instead of?
I don't know what's going on. I do know that they're changing or already have an insider preview. The blue screen of death itself doesn't even look the same anymore, and it's like green too, at least on my machine. But I'm not super aware of it. I know that there's a lot going into that with the resiliency initiative, and then as well, a bunch of features have got added in, like hot patching, where you can do some of this interesting update on the fly stuff.
Here we have, do you think EDRs will be moving to the hypervisor in the future with all the BYOVD and kernel exploitation threats?
Could be. I'm not at liberty to say because I don't work currently for an EDR vendor. But just in my opinion, I don't think that gets you very much, because if people were enabling the tools which exist right now, like that Microsoft gives you, you're enabling HVCI, you're enabling the driver block list, you're enabling your own code signing policies. You're enabling some of these best practices, secure boot, just all of this stuff in general. That right there is going to alleviate a ton of this stuff. I think it just goes back to, in general, the whole you need admin to do it. I know there's two camps, right? There's a camp that this is a cop-out saying that, oh, admin to kernel is not a vulnerability. And then there's a camp that's like, look how many people are widely abusing this. I'm probably somewhere more towards that we need to do something about it. There are some EDR vendors that exist which do have some kernel blocking capabilities. CrowdStrike has a blog on it from whenever I was there originally, from a feature that the team created surrounding like that platform in general. So like, I only say that because EDR vendors are looking into this. Obviously, it's something that they deal with. It's something that all folks deal with in general. But as far as what your first point was about moving to the hypervisor, I just don't see a need to, really, when you have Hyper-V and things such as this, because it's like, okay, let's say you're a vendor and you do install hypervisor. Now what? What are you looking to do with that? You're looking to prevent unsigned code execution. Okay. You're looking to prevent some drivers being loaded. Okay. You have both of those features already in the Microsoft ecosystem, and it comes natively, right? So I don't see really them going in that direction in general. And I think in general, like, you see some of this stuff coming out where a lot of folks, like Mac, for instance, basically worked with vendors to move out of the kernel. Linux, eBPF and all that moving out of the kernel. It doesn't make sense for all of this ingenuity to be going into, let's get people out of the kernel, only to go, no, vendors are going to go even lower level into the hypervisor. But again, I'm an imperfect person with imperfect opinions. So just my opinion on the matter.
It's funny, I was just talking to a vendor yesterday called Valley Cyber. They got a product called Zero Lock, but it's for it's like hypervisor protection, especially against ransomware and such, for ESXi servers, so specifically VMware. But thought that was interesting timing for that question. They were claiming that there's been a lot more attacks on hypervisors on the ESX side.
Interesting.
All right, there was a couple more philosophical.
And I'm happy to go through all of them. I like talking about this stuff. So.
Let me find it here. Where is it? This one's more of a, I don't think that's a question. That's just more of a statement. I guess, are you worried there won't be any bugs left due to AI? But that's...
AI can launch a similar debugger now. You can literally ask headlessly fuzz V8 and find you, are you worried there won't be any bugs left? No, I'm not worried. And that's probably a little bit of me being naive, and probably because I still think AI is very much in the infancy. Like, obviously it's going to get better and more improved. But if that were the case, if like bugs were all going away, we would see en masse everyone being fired from security, which people can say what they want. In my opinion, I don't see a lot of. I still see companies hiring and whatnot. So AI does make things scary. You're like, oh goodness, is there going to be enough bugs left? Is there going to be enough, this, that, and the other? I don't really have an opinion on it right now. I'm not really huge on AI, personally speaking. Just like this, for this specific line of work, I guess you could say. But it's definitely interesting to see what this stuff does. I just, like, people like to... and this might sound controversial, people like to throw themselves on every little hill to die on. I just kind of block that, block it out, so to speak. I just don't look into the AI stuff all that much, because you see two camps. You see people like, oh, it's over, it's completely over. And then you see people that are like, oh, AI is the dumbest thing in the world. I'm probably somewhere in the middle. So I just don't let that stuff, bother me. Maybe that's a bit of, privilege on my end, just given where I'm at and what I'm doing. Maybe, someone else who's been let off or whatever has a different opinion. But I just kind of block that stuff out and focus on the stuff that I'm interested on. And, if there's no bugs left eventually, then, it was meant to be. There's no bugs left. We'll move on to something else. I mean, how many times do you hear Steve and whatnot talk about, 2013, all these, use after freeze and Internet Explorer and stuff, and then it all dries up. People move on to the next thing and the next thing and the next thing and the next thing. And I think
the good old days.
Yeah, exactly. There's always going to be that next thing. In my opinion. But again,
yeah, and I think with, like, remember OpenAI announced Aardvark, and there's a lot more people doing SaaS, like AI powered SaaS, and then DAST on top of it to do validation. So I'm hearing a lot more pen test consulting companies and just developers in house using that, and they're all saying the same thing, which is we're finding bugs of code we've tested for years with the AI powered SaaS. So, like, especially low hanging fruit, like web based bugs and stuff. I think it's definitely going to strip out a lot of them. Those bug bounty programs like HackerOne and BugCrowd, all that low hanging fruit, that stuff should be easy to get anyway. So it's just going to keep raising the bar. I mean, you saw Project Zero originally with nap time and then big sleep. They started to get better and better results. And we saw what it was at the red team at Anthropic last weekend say that they found 500 critical 0 days or high 0 days using AI. So doing a lot more AI fuzzing and instrumentation with all being, it's amazing when you watch these agents without even being told to then decide to run a debugger and run a disassembler and then do this and that and do validation. And it's going to get better and better if it's going to raise the bar. I think, and also, like, AI brings a whole new attack surface. Like, look at some of the Claude stuff that came out recently, where it access to your file system, it can tidy up things and all that. Like, that's getting into excessive agency, and if you can exploit the fact that it's crossing new trust boundaries, and we all know how we can jailbreak and prompt inject and things, like, I imagine there's going to be some pretty significant breaches caused by this type of stuff in the future.
Yep.
All right, there was where is it? I know there was more. I don't want to be dumb and post the same one up twice.
Oh, no worries. This is getting into a bigger one. It's not super technical, but it's a great question, and people have this question a lot. I'll read it real quickly for those just listening. How does someone get from beginner up to the level where I can truly understand at this level, referring to what Connor's doing, and how to research? Is there a pathway that you've put together to do so? Yeah. So again, and I'm not saying it to be self-deprecating, I have my own opinions. I'm imperfect. I realize that everyone's got, their opinion on the matter and whatnot. I can say for me, it can't say for anyone else. But like, for just like let's say exploitation in general, or just low level systems or stuff like that, a lot of it is tenacity. And what I mean by that is what I don't mean by that is staying up 24 hours a day. What I mean by that is like the canonical example I give is one of my heroes, Morton Shank. He works at Offensive Security. He did a Black Hat talk in 2017. I think it was 2017, and DEF CON in 2017. Like, I just literally, that video that he posted, I listened to it. I understood absolutely nothing. I literally watched that video probably 50, 60 times in a row. And like, I would pause it halfway. I would pause it halfway through, and then I would go Google, okay, he said this. And then I'd get on this other blog and I just read through until it started to make sense. Now, is it privileged to say that in the sense of like, there's people that I know that I can rely on to ask questions? Absolutely. I'm always happy to answer questions. I know that there's others too, but that's what I mean. It's just, it sounds so cliche, but it's just like, I think people get discouraged a lot. They hear something and they don't fully understand it the first time. And you just have to keep over and over and over and over and over. And you also have to have in my opinion, you have to, not that anyone else doesn't have a passion about this, but like for me, I don't like video games really. I just don't. I've never liked video games. I like doing this stuff in my free time when I have time. I think that factors in a lot too. I also know that there's people way smarter than me, and I'm fine with that. So tenacity is number one. And I think I tell everyone, start a blog. Literally start a blog, because when you start a blog, you're associating your name with something. And when you associate your name with something and you're teaching someone something, you want to understand it a lot better than just you understanding it. Take notes. Like for this presentation, like I didn't just wake up today and start doing this. Like for the last 2 weeks or whatever that I've been talking with Steve, like every night, like I'm telling my wife, like, okay, I'm going to spend 45 minutes here, an hour here, just preparing stuff, getting the demos ready, looking through, making sure I fully understand stuff, going back and rereading Windows internals books, all that good stuff. So I recommend everyone just start your own blog. Even if no one views it, even if no one does anything, someone one day might view it. And when you put that kind of self-pressure on yourself to know, okay, well, if I'm going to do a blog, I have to understand it better. If I want to understand it better, you should all, it's not as simple as saying you should be able to explain it to a 5-year-old. I think that's it's not applicable really, to these lower level things, but just being able to explain it to a stranger who may not be able to understand every technical detail, but goes, okay, yeah. Like I have blogs on edge exploitation. Probably not the most technical thing in the world, but it's like a 350-minute read blog. That's not because it's got 350 minutes worth of technical content, although maybe it does. It's because I like to reiterate. I like to give examples, analogies. And so it probably sounds like I understand it better than I do, because I don't explain it the way that I understand it. I try to explain it the way that I would explain it to myself had I not already had this knowledge previously. So I think a blog is a great way to do that. And just being tenacious are the two main things. There's lots of resources out there. We could list them all. I mean, Windows internals books, like just reading them, everyone makes fun of the example of their monitor stands. But just reading them a little bit, like pick a topic in there that's interesting. Like look at the table of contents. Oh, how a process is created on Windows. Okay, I'm going to go through this flow. It's like, oh, okay, I'm going through the flow. Let me start up a debugger and look at this. I don't know how to use the debugger. Microsoft has tons of documentation on it. There's lots of other good books out there. There's courses out there. I mean, there's tons of free content out there in blogs. And I think that's one of the best things that you can do. And unfortunately, we're seeing a lot less of that, to belabor the point, because in this technical space, these kind of bugs are worth lots of money. People don't necessarily put out blogs anymore, and it's hard to do that. In no way am I trying to virtue signal to say, oh, I would never, I like money. Everyone likes money. Like, it's not what I'm saying. What I'm just saying, though, is I like blogging. I like communicating, because how do I know what I know? I know it from Alex Ionescu or, all these other folks who have done tons of conference talks, blogs, all this stuff. And I feel like I want to do the same thing. So blogging, being tenacious, and just tinkering. And like people get scared. Oh, I don't want to post a blog on 32-bit buffer overflow. Do it. Who cares? Yeah, there's a million of them out there, but maybe you bring a new perspective. Maybe you show how to do something different. And again, it's about building up a corpus of work and being able to articulate things to others. And once you have that mindset, it helps you when you're learning from others, if that makes sense. Questions to ask, things like that. So yeah.
Yeah, like I've gotten quite a few people hit me up and say, oh, the way that you explain things in the videos is a lot more helpful to me than how I've heard other people explain it. So just like Connor said, the way that you're learning it and going through the pain of figuring things out and then explaining it might be exactly the way it makes sense for somebody else. That's exactly why I say thanks to like Richard Johnson for keeping frack alive, because like you were saying, there's just not as much research being posted as it used to. And it's to be fair, it's a lot harder now. The attacks are different. You know, you reminded me like the tenacity, like going back in the early 2000s. I don't want to age myself, but I remember I would always see FS : brackets 0x30, and it was in like a frac art, but nobody ever explained what it was, and Google didn't know what it was. There was like you had to go figure it out. Like, oh, it's the TID pointer. Jeez. You know?
Exactly. Just stuff like that. Exactly. And it's tinkering, and people have this expectation too. At least I do for myself. I'm biased. Like, I'm going to sit down, I'm going to do this for an hour, and I'm going to understand it by the end. When I say I watched that talk by Morton 50 or 60 times, that was like over the course of like 3 weeks, you know, during COVID. Like, that's when I started during COVID, like all this. And you're just going and going and going, like, that makes sense. Okay. And it's not the first time you listen to it. It's not the second time. It's just like you said, the tenacity to go back and tinker with stuff, and maybe you don't fully understand. And, you know, there's a lot of people out there who are willing to answer questions and help too. So.
Yeah, exactly. And, you know, not everything always, you know, there's moments, the eureka moments, I guess you call them, when something finally does click that you've been working on it. It's just like, it's so validating. It's like, you get a little
And everyone, when you have that moment, go blog, go do that, go put something out. Like, here's how this works or whatever, and help someone else out. And more importantly, help yourself out.
And even the moments when you fail, like, that's a learning opportunity too. Like, I remember there's this one use after free bug that I found with IDA by static analysis, and I was like so convinced that you could exploit it. And there was a JavaScript like exception handler blocking it from being the code from being reachable. It was like dancing in the background, giving me the finger. I'm like, I spent so much time trying to work around that, but I never did. And it's burned into my brain.
Exactly. And I think that's all important too for blogging as well, not just showing the success path. I try to do that a little bit in some of my blogs, like ask rhetorical questions like, now you're probably thinking, why did I not try this? That stuff is very important for blogging and whatnot, because it's, you know, taking the logical conclusions you would think someone else would make and explain why you can't do that, and not just the worst thing that you can do. And the more, what I found is the lower level you go, which I have a long way, like there's a lot more low level stuff that I have no idea about. All the blogs that exist on it do not have the same level of explanation. It's like you see a call stack, and then the next image is a call stack in a completely different thread and a completely different process. Like, how did you go from that to that? I think being able to, it's a skill, is being able to take those things. I forget who was talking to me about it before. I was talking about it with my friend Jordan, because I posted something a long time ago. I'm like, I have this weird structure and it's doing this weird thing. And she responded back to my tweet, and she's like, you have an unsigned long as the first member of your structure, don't you? I'm like, how did you know that? How did you, you know, that honestly is a skill. So tinkering with stuff, being able to look at stuff that maybe isn't fully explained, and then giving back to explain it fully. That's what makes someone valuable, in my opinion. Oh, I think you're on mute.
Thank you. I was going to say, and making good use of detailed notes, like when you're going through IDA and working on something, detail, save, because going back, you'll never, some of this stuff is so deep that it'll take you just as long to get back into the context because you didn't document it, because you didn't remember. We'll take this question, and I think we'll finish up here. I'll post it up here. I'll read it for folks listening on. Previously with Dr. Bramwell, he came on and shared the Sharam shellcode framework, and he's doing some amazing research now as well. But there was a discussion about Microsoft investment in security mitigations, giving SK kernel and Hyper-V makes modern exploitation hard. Is there a similar trend here?
What trend does this person mean? Previously, there was a discussion about investment in security mitigations. I'll try to understand the question. Do you mean investment in security mitigations in Microsoft in general because these things exist? If that's the case, I think the general notion is no. And I'll give some examples of that. We've actually heard of things. So there is actually something which I talked about in Black Hat called extended control flow guard. So control flow guard exists, and there was something called extended control flow guard, which was an amazing mitigation, like for what it was, because what it did basically is control flow guard has an issue where you can call any valid call target. And because, Windows has everything so modular, like kernel 32 has to call something kernel based, all exported functions are valid call targets. And so what you could do, like you have a ROP chain or something like that, or not ROP. Let's say you have a function pointer override. You can still override a function pointer with virtual protect. You can still override it with, you have to find some way to control the arguments to that function, but you can still override it with those functions because those are valid call targets. So that's called coarse-grained CFI. Microsoft wanted to go fine-grained CFI. Only developer-intended call target should be called, and they had this thing called XFG. They used the prototype of the function, created a hash of it, and used that to validate. Really cool. Got completely deprecated. And you've heard some talks from Dave Weston and others saying basically, we're not really investigating in the mitigation space anymore. I'll give you a really good example. There's something called user mode accessors, UMA, on Windows. It's a very new thing. No longer are you going to be able to just provide a user mode buffer like from user mode and have kernel write to it like it's the case in system calls and stuff. There's a ton of validation that's done now. This is so eventually in the future, SMAP can be implemented on Windows, which SMAP already, the bones of it are there in preview builds. It just has not been enabled due to some CPU features on newer machines, but the bones are all there. Like that's the kind of stuff I more see, architectural things like here's how we did it before. Now drivers need to use these user mode accessor functions in order, like whole paradigm shifts almost, I think is what is the trend that we're going to see. We see this a lot with Microsoft moving things, like I said in the beginning of this talk, into the Windows endpoint security platform. Basically working with vendors to get out of the kernel and move into user mode. Those are the things I think we're going to see less of XFG, ACG. There are so many mitigations already. Like if you really looked at all the mitigations, like
there's dozens.
You can, like, even in, like, if I just share this real fast, last thing that I'll do, if I just share this debugger right here, and I just do cur process.kernelObject.mitigation flags values. That's just one of the mitigation flags. Those are all the mitigations. Oh, you want more mitigations? Okay. Mitigation 2 flags. Look at all these mitigations that exist. Oh, you want more flags? Okay, let's go to 3. Then you have even more than that. And you have other mitigations which aren't even managed by the process object, that are managed by the token, like redirection guard and some of these other things which you really don't hear talked about so much. So there are just so many mitigations out there as my point. It's like, what more can you do? Shadow stacks, and like there's a new thing now called HLAT, hypervisor and linear address translation. One of the previous things you could do was, let's say you had a read-only page of memory that's protected by the slat table in VTL0. You could remap that memory to writable memory. Nothing's stopping you. You just use the page table entries to remap the memory to something writable. Satoshi Tanda has a good blog on it. HLAT is probably one of the last mitigations we'll see that's from the CPU vendor that truly ends the end of a lot of this code execution stuff, because you can't just remap memory anymore into something else. The page table translations are validated by the hypervisor. So I don't think that's going to be the trend. I think it's going to be paradigm shifts, like user mode accessors, Windows Endpoint Security Framework, all this stuff going forward.
Yeah, like memory tag extensions on ARM and stuff. Some of these things are,
and that's coming to x86 too. I have a tweet from a little while ago, maybe a few months ago, where I saw an insider preview build on x86. Memory tag is now a field. Actually, let's see if it's a field. NT MMPTE hardware. Did they take it off? Yeah, it's not here right now on this version of Windows. But one of the insider preview builds has memory tag on x64 machines. For x86, AMD released a blog, I think it was, like even outside of ARM, bringing memory tagging into x86, like in the software level, I think is something that they're looking into doing or enabling that. And like you said, yeah, ARM has awesome mitigations. Pointer authentication, I did a blog on reverse engineering pointer authentication on ARM, like the Windows implementation, like how it works in Secure Kernel, how it works in user mode, how it works in NT. And MTE, like you said, on ARM systems. Really cool mitigations. You can see there's some more paradigm shifts. They're not like DEP or, ACG or some of this other stuff. It's just like completely nuke this class.
The one you were mentioning, user mode, what was it again?
Roles, pointer authentication?
No, to stop the kernel from writing into user mode buffers and stuff.
Oh, user mode accessors. So
that sounds like it's going to stop like double fetch kind of bugs.
Yes. So user mode accessors. I'll send it in this chat. It's documented by Microsoft now, and a lot of the functions are in the preview builds of Windows, but it's documented. And exactly, it goes through and talks about why this is why you need to use this to avoid double fetch and all these kind of primitives, which aren't always apparently transparent. This one just comes back to driver development and knowing how to deal with these issues, which may not look like they're much, but can definitely lead to some race conditions and whatnot. So Microsoft's documenting that with the ultimate goal of SMAP being fully enabled on Windows. And the way that will work is SMAP will have dedicated writer functions via user mode accessors, which disable SMAP, which is an E flags on a thread, disable SMAP, do the write, re-enable SMAP. So then you can always have SMAP enabled, and anytime like an attacker would try to do a data copy into user mode, SMAP would block it. But again, that's not fully enabled yet on Windows, but the bearings are there, the functions are there in some of the insider preview builds.
We left with logic bugs, nothing else. That was good.
Yeah.
Cool. All right. Thank you so much. I really appreciate it. Like, it definitely shows that you've been working hard to get these demos ready and everything. They work pretty much flawlessly. So amazing stuff.
Appreciate it.
Next week, I'm going to post this on X soon. We've got Graham Helton coming on. He's going to do a live demo of the authorization bypass vulnerability he found that allows for remote code execution in any pod in the cluster from a commonly granted read-only permission, like containers and such. So that's going to be a really cool one. So cool. I will get that out soon. But thank you again, Connor, so much for
thank you.
Appreciate it. Always love to have you on. And everyone else, have a great, well, you too, Connor. Have a great weekend.
Thanks, everyone.
Bye-bye.